Hey everybody, welcome back to the third chapter or the third lecture in our Chem 20 series, Matter and Energy. So everything that you can see in your room, in your office, wherever you are, is made of matter. Different kinds of matter are related to the differences between the molecules and the atoms that compose that matter. And uh, molecular structures, right? Water molecules here on the left, carbon atoms here on the right. All of this stuff is defined as matter. Now, matter is everything that occupies space and has mass. The only things that don't occupy space or have mass are like photons or, energy waves. So some types of matter, such as steel or water or wood or plastic, obviously we can see those things with our eyes. Other types of matter, air, microscopic dust, this stuff's impossible to see without some sort of magnification, right? And so matter, we know with our imaginations, we know that we have to use to kind of picture these things, or with instrumentation like microscopes, we are able to see that matter is actually, while it may appear smooth and continuous, it is not. It's composed of atoms. And these are submicroscopic particles that are the fundamental building blocks of matter. In many cases, these atoms are bonded together to form molecules. Two or more atoms together give us molecules that we went over in the last chapter. And these will have certain specific geometric arrangements, and we haven't gone over those yet. Now, recent advances in microscopy have allowed us to get good images of atoms and molecules, and so we can see here. Now, these aren't real images; these are computer-generated images here. I'll show you some real ones in a second. But atoms and molecules, you can see in this aluminum can. These aluminum atoms, they exist as independent particles. Every one of these atoms is an individual aluminum being, and all together they make this macroscopic object, the can. There's also well-defined molecular particles. So what we were looking at just now is an independent atomic particle. I guess I'll write that down. Atomic particle. We have molecular particles as well. Molecular particles. Now, all matter is ultimately composed of atoms, but in substances such as rubbing alcohol, several atoms are bonded together in a well-defined structure. So, atoms give rise to molecules, and we have matter of both types. We have atomic matter, we have molecular matter. Now, with the help of scanning tunneling microscopes, we're able actually to see a lot better, or the resolution of our microscopes has gotten to that where we can make out the outsides of atoms. If we try to use just regular light, then this basically we get stopped around in the micro world, about 10 to the minus 6, 10 to the minus 6 meters. To see into the atom world, we need to get into the nano or picometer range, and so for that, light just doesn't cut it. We need to use something a little smaller, smaller wavelengths, and for that we use electrons. All right, so a scanning tunneling microscope, or an STM, creates the image that we're looking at here. It scans the surface with a tip that has just one atom on the tip, so like a little needle that has one atom, and then you kind of scan it back and forth over a surface, and that one little atom will detect all the other little atoms as it passes over it. And we see these atoms as bumps. So these are nickel atoms. And then this is on the right, a scanning tunneling microscope image of DNA. This is the hereditary material that encodes the operating instructions for the cells in your body. The DNA is in yellow, so you can see that there. It's double-stranded structure, and you don't really see the double helix here, but we do kind of see the multiple strands. Okay, let's talk about the phases of matter. Matter comes in a couple common phases here on Earth anyways. The states of matter are solid, liquid, and gas. Now, matter can be classified according to its states. So we say things like solid, liquid, gas, and of course there's also a plasma that exists like on the surface of the sun and in lightning bolts and stuff like that. These are highly ionized particles in really hot kind of gas-like state, but different than a gas. And then there are some overlapping areas where we get, like super solids or what's the other word? We get gases and liquids that sometimes behave together. What do we call those? Superfluids? We might get to it in a different chapter. I don't know if it's at the end of this chapter. But the common states of matter, solid, liquid, gas. Now, water exists as ice, a solid, liquid, just regular water, and gas, steam, right? And so we are familiar with at least the three different phases of matter for one particular compound, water. Now, in ice, the water molecules are spaced closely, and although they do vibrate around a fixed point, they can't generally move around each other. And so there's no motion happening in the solids. Now, the vibrational motion always exists. At any temperature above absolute zero, we are going to have, so that's 0 Kelvin, we are going to have some vibrational and maybe rotational motions. But translational motion, which is moving from one spot to another spot, doesn't come in solids. Now, in liquid water, the water molecules are closely spaced, but they are free to move around each other and past each other. So this is where they get that translational motion. They can still spin in space, they can still vibrate as well. In steam, water molecules are actually separated by a large distance. They don't interact significantly with each other, and we can say that these actually have a lot more space in between them than in the other two phases. So as far as the compressibility, which we'll get to in a future slide, since these two are already as close together as possible, we can't compress them very easily. But these guys, gases, these can be compressed. Okay, so as far as solids, let's expand on solids a little bit. So in solid matter, atoms or molecules pack together. They're in fixed locations. Fixed locations. The neighboring atoms or molecules in a solid, they vibrate, they oscillate, they don't move around. Solids are what we say fixed volumes. They have fixed volumes, meaning if I have 3 cubic centimeters of aluminum, I still have 3 cubic centimeters of aluminum no matter what container I put it into. It doesn't expand or condense. They also have a rigid shape. They tend not to change their shape very often. And we'll give you some examples in a second. Now, ice, diamonds, quartz, iron, all of these would be solid matter. Now, it comes in two flavors. We get crystalline solids and we get amorphous solids. Crystalline are atoms or molecules arranged in a geometric pattern with long-range repeating order. Amorphous solids are atoms or molecules that do not have long-range order. So an example of a crystalline solid would be a diamond or sodium chloride, NaCl, table salt, even sugar, right? Rock candy, for example, or granulated sugar. These are little cubes, little crystals. So these are examples of crystalline. Now, an amorphous solid would include glass. It would include rubber. It would include plastic. I would say toothpaste, possibly, but depends on if you think toothpaste is a liquid or a solid. It's probably a solid, but we can talk about its actually, I was going to say its viscosity, but viscosity is a liquid property, so maybe I'm not completely in the solid camp there with toothpaste, but it would be definitely amorphous if we called toothpaste a solid. So, yeah, you can see in these images here exactly what amorphous and sort of crystalline mean in terms of the long-range order. Let's talk about liquids. Liquids are, well, I said liquids, but I don't have a slide for liquids, so just kind of listen to what I'm going to say here. So for liquids, the atoms or molecules are close together. They are free to move around each other. So liquids have a fixed volume because their atoms or molecules are still in close contact. But liquids actually will change the shape or take the shape of their containers. because those atoms are free to move around, or those molecules are free to move around. So we can say here, in terms of shape, solid is definite, volume is definite, in terms of these two features. For liquids, shape is indefinite, but volume is still definite. And then for gases, we will see that they are different. Water, gasoline, alcohol, mercury, all of these are examples of liquid matter. Now for gases, the atoms or molecules are separated by large distances. And because of that, that means they're not in contact with each other. And so that means we could, if we wanted to, push them back into contact with each other. So they are compressible. Gases are compressible. Solids are not, gases are. Now gases will always take the shape of their container, and they will always fill their container. So gases have volumes that are indefinite. So if I have a small amount of gas inside of a little box, and then I put that box inside of a big box and I open it, the gas is now going to be inside the big box when it was inside the little box. Gas is spread out. Okay. Oxygen, helium, carbon dioxide, these are all examples of gases. Okay, so those are the common states of matter. Now let's classify matter according to composition. We have pure substances, and then we have mixtures. So before we get into the differences there, let's go into what the different types of pure substances are. So pure substances are composed of only one type of atom or one type of molecule. So this here is a balloon full of just helium atoms. Helium is an element, right? So if the only thing you have inside of your container is an element, then that's a pure substance. Elements can't be broken down into simpler substances. No chemical transformation can decompose an element into simpler substances. We will talk about what is inside an atom later. I know that there are subatomic particles, but these are not new substances. And if we break all of the atoms down into their subatomic particles, well then they are all exactly the same. There are no elements anymore. There are just protons and electrons and neutrons, or quarks, or however deep you want to go. So element is as low as it gets before you start to lose any kind of sense of an atom. All known elements are listed on the periodic table, and the periodic table can be found inside the front cover of your book. They're also listed in alphabetical order on the inside cover of the inside back cover of the book. So yeah, so elements, easy to find, because if you find it on the periodic table, then it's pure substance. Now let's talk about compounds. A pure substance composed of two or more elements in fixed, definite proportions is a compound. This is the definition of a compound. Atoms found in a fixed, definite proportion. Now, compounds are more common than pure elements. Most elements are chemically reactive and combine with other elements to form compounds, and the Earth is old, and so these have had lots of time to do that. Water, table salt, sugar, all examples of compounds. Now, compounds can be decomposed into simpler substances, right? Because they are made up of atoms, made up of elements. Water can be decomposed into hydrogen and oxygen. Table salt into sodium and chlorine. And so a compound can be decomposed where an element cannot be decomposed. Okay, so water. Water is an example of a pure substance because it is, so again, pure means it's the only thing in there. You don't have anything but one type of something, either one type of atom, one type of element, one type of compound. And so if your solution only has, bad term, solution means mixture. If my liquid is pure water, then it's or if it's only water, then it's a pure substance. If it's only vinegar, then it's a pure substance. If it's only ethanol, right? If it's 100 proof vodka, only ethanol, then it is, or was it 200 proof? I forget how that goes. Then it's only one molecule, one type of molecule. It's a pure substance. Okay. So if you don't have a pure substance, then you have a mixture. Now, mixtures are composed of more than one substance. It can be two types of atoms, two types of elements. It could be a mixture of multiple compounds, okay? But the difference here is that a mixture is composed of different substances that are not chemically united, but simply mixed together, okay? Sorry. And here's an example. Air and seawater. Air and seawater are both examples of mixtures. Air contains primarily nitrogen and oxygen. There's other gases in air, but those are the two main ones, and so it's a mixture of multiple gases. Seawater, primarily salt and water, but we know there's lots of stuff dissolved in salt water or in the ocean water. But those are the two major components, and so we can see here, right off the bat, it's not a pure substance because there's more than one type of something, more than one type of stuff, more than one type of gas molecule, more than one type of, compound or atom. So these are mixtures. Now, where pure substances could either be elements or compounds, mixtures can either be homogeneous mixtures or heterogeneous mixtures. Okay? I've got a table for you. So the terms are here. Homogeneous here means that everywhere we look in that mixture, we're going to find the same ratio, the same proportions, the same set of stuff. Whereas in a heterogeneous mixture, depending on where we look, we might see different stuff. So some examples. A heterogeneous mixture of oil and water. So it's clearly a mixture, it's got two different things in it. The difference is, if we look on the top, we're only going to see the oil. If we look on the bottom, we're only going to see the water. Another example, some Cheerios, right? If you take a spoonful of Cheerios, you might get all Cheerios. You might get all milk. You might get half and half. That is going to be a heterogeneous mixture because not every spoonful is identical, right? And there are times when you could just have one component or the other. Try that with, chicken noodle soup puree, or some kind of pureed food, right? Or some kind of, in this case, like a broth. This is maybe tea. This could be whatever, any kind of drink. Anywhere you look, you're going to find the same ratio of dissolved stuff. So homogeneous here actually has a good definition. Homogeneous is thoroughly mixed or evenly mixed, where heterogeneous is not thoroughly or evenly mixed. Okay. Another example of a heterogeneous mixture would be a salad, right? Depends on the salad, I suppose. And so then going back real quick to these, would these be homogeneous or heterogeneous mixtures? What do you think? Air, homogeneous. Can you imagine if walking around, sometimes you walked in and out of patches of oxygen? That would suck, wouldn't it? Where you're just like, oops, I got to find me a patch of oxygen because I guess I'm going to die if I don't find some oxygen here. We're lucky that our air is completely, thoroughly mixed and all of the oxygen atoms spread out so that no matter where we go, there's some. That's not always the case locally, right? If there's a carbon dioxide vent pouring carbon dioxide out, there's going to be a local high concentration of carbon dioxide there. But we're talking about mixtures at large. So when we talk about the air, we're going to assume kind of an average air. Same thing with your blood. Your blood is homogeneous. Okay, salad dressing, Italian salad dressing would not be homogeneous. Okay, let's shift gears now. We've talked about mixtures, we've talked about pure substances. Let's talk about the different kinds of properties that different kinds of matter can have. So physical properties are going to be ones that that a substance can display without changing its composition. So I'm going to I guess I'm kind of starting with physical and chemical just kind of thrown out here, but let's just kind of define them first. So a physical property is one that the substance displays without changing its composition. A chemical property is one that a substance displays only through changing its composition. So for example, water here, boiling, going from liquid to gas. It's still water. So the physical property here might be the boiling temperature. The boiling temperature of water, 100 degrees Celsius, right? Or 212 Fahrenheit. This would be a physical property because we get to see the temperature that this happens at, but the water molecule has stayed a water molecule. So it hasn't changed its composition. Now let's compare that with a chemical property. We see here that iron atoms can rust. They can rust, and the process of rusting means that embedded in all of these crystal lattice of iron atoms is now oxygen atoms. There's some oxygens in here, and the iron has become iron 3. So this would be iron 3 plus, and we would have some oxygen 2 minuses, and then so this would be Fe2O3. This here composition has changed. It's no longer all irons. It's irons and oxygens, and the iron isn't even the same iron. It's an ionized form of that iron, iron 2 plus. I'm sorry, iron 3 plus. So to see the rusting, we had to change the compound. So rusting is a chemical property, whereas a boiling point or a melting point would be a physical property. Let's keep going. The characteristic odor of gasoline, for example, is a physical property. Gasoline doesn't change its composition when we smell it. The same is true of butane. Butane from liquid to gas form doesn't change its form. And so just becoming a gas molecule, us being able to smell it because now it's in our nose, doesn't change its structure. Now the flammability of it, whether or not it burns, definitely changes the structure. If we try to burn something like a piece of steel, it either burns or it doesn't, right? And steel doesn't really burn when we put flame to it. So we wouldn't see anything, and so we go, oh, so it's not flammable. And then we'd look at the iron and go, or the steel, and we'd say, oh, and it didn't change its composition. So we wouldn't actually learn anything there. We would just see that it's not flammable. In this case, though, the gas does burn. This butane or liquid butane burns. When it burns, it becomes something new. It becomes water and carbon dioxide. And so seeing that it burns and then checking its structure will let us know whether this was a physical or a chemical change. So a chemical change would be something like burning. The atom or the molecule composition has to change. Now, so water boiling is a physical property. We can talk about state changes, and that's kind of what I'm showing you here. So a change in state is a physical change. So physical changes, it's already said, it's already written here. State changes. So that means liquid to solid, solid to liquid, liquid to gas, right? Gas to liquid. These would all be state changes, and these are always physical changes. Copper also rusts, turns green like Statue of Liberty when it rusts. I'm going back here real quick because I want to talk about the equation that we usually show for chemical reactions. We don't show these for physical changes, but for chemical changes we do. And for chemical changes, because the substance is different afterward, we often categorize the initial substance as the reactant, and then whatever we end up with at the end as the products. Okay? So when matter undergoes a chemical change, we have our reactants becoming products. Now, the differences between physical and chemical changes is seen at the molecular and atomic level. Okay? And so these aren't things that we're going to be able to see, but we're going to have to rely on instrumentation and evidence to help us kind of believe this stuff. Now, when I show you pictures, of course, that'll be easy to see, or if I tell you the substance stays the same, but you may have to use your imagination a little bit. If I tell you ice cream, frozen ice cream, and then liquid ice cream, is that a physical change or a chemical change? You're the one that has to imagine if those ice cream, quote-unquote, particles have changed or not, right? Just because now they're able to move more than they could move before. Physical changes result in a different form of the same substance. A chemical change gives you a completely new substance. So if you think the ice cream tastes the same when it's melted compared to when it's cold, then it's probably the same stuff. So vaporization is a physical change. Burning is a chemical change. Let's talk about how we can actually separate mixtures based on physical changes, because that's a nice little trick that we can do in the lab. So there's a couple of ways. One is called distillation. Distillation involves having a mixture of liquids, and the liquid with the lowest boiling point will actually vaporize first. And so what you do is you've got a mixture in here, let's say of A and B. Let's say that A boils at 70 degrees and that B boils at 85 degrees. So if we heat this up slowly, we can get all of A to boil. And maybe some of B starts to boil, a little bit of B will probably boil. But the point is that some of it, as it starts to climb here, it should condense on the walls of this glassware and just drip back in. And all of the A, which is boiling more often, will find itself being a gas longer. And then this is called a condenser. We've got cold water running through here, running through this whole thing. And that helps to cool the gas back into a liquid so it can drip into this container. So distillation is actually how you also improve the alcohol content in a beverage, right? You boil out the water, leave the alcohol. I'm sorry, that's a lie. You boil out the alcohol, it boils first, and you collect it. That's dangerous because it's flammable, so you shouldn't do that. In fact, it's illegal to distill in your own home. Okay, so that's distillation. Good for separating mixtures of liquids. What if you got a mixture of a solid and a liquid? Well, that we can use something called filtration, right? I mean, we could also take like a solution of, so the lines, the liquid, and the little dots are the solids, and we could heat this, right, with a flame, Bunsen burner or whatever, and yeah, we could get all the liquid to leave and then just have the solid left behind, but that's not really separating a mixture. That's just getting rid of one of your things, and so that's not. So we could do that though. We could evaporate a liquid and leave the solid behind. And we do that in one of the labs that we do to separate the salt from the water, salt from salt water. But we can filter, and that means just pouring the liquid-solid mixture through some kind of filter that will trap the solid or trap particles based on size. You probably do this in your kitchen when you use a colander, or if you strain spaghetti or whatever. So filtration is a method. Also, we have one called decanting, which is something similar to this, but it just doesn't use a filter. You just take your mixture of solids and liquids, and then you just kind of tilt it on its side, and you pour all the water out, and you leave all the solids behind. Like if you ever strain the water out of a can of peas, that's decanting. Okay, let's talk about the conservation of mass. Yikes. Conservation of mass. So there is no new matter. Matter is neither created nor destroyed in a chemical reaction. In nuclear reactions, mass changes do happen, but chemical reactions, not the case. We'll talk about nuclear reactions towards the end of the semester. So we can't ignore mass changes like we can in nuclear reactions. I'm sorry. So what I'm saying is, in chemical reactions, any changes in mass are so tiny that we can ignore them. They may change. This has to do with the nuclear aspect of it, but we're not going to get into that. So during physical and chemical changes, total amount of matter remains the same. And you can see that here. So if I had 58 grams of butane and I combined it with 208 grams of oxygen to make 266 grams of products, I'm sorry, reactants, thinking ahead, then I should still form the exact same amount of products. Now they're going to be different compounds, carbon dioxide and water. This is a typical problem that I like to give you guys. I'd like to, just leave one of these values out. I'll say 58 grams of butane reacts with X amount of oxygen to form 176 grams of carbon dioxide and 90 grams of water. How much oxygen was there in this reaction? And you just add up the one side and then figure out what you're missing from the other side. Easy peasy. Okay. So like mass, we have something else called energy. And I guess I shouldn't have said like mass because it's nothing like mass. But what is like mass is that there's a law that conserves the amount of energy that exists. And so That was my transition into this next topic about energy. So the behavior of matter is actually driven by energy. So we need to talk about energy. Now, energy is the main component. Energy is a major component of our universe. It drives the whole thing. It's the capacity to do work. And so anything that moves, anything that does anything has energy being fed into it. I mean, anything that vibrates has energy in it. Work is defined as the result of a force acting on a distance. In fact, we can calculate work as just, oh man, it's something times d. What is it? I've already forgotten what it is. It's a force on a distance. I'm just going to say it like this. Force times a distance, where F is a force. Anyways, we're not going to worry too much about work, but we are worrying about energy. So the behavior of matter is driven by energy, and to understand chemistry, it's critical that we understand a little bit about energy. So like matter, energy is conserved. There's a law of conservation of energy that states, energy is neither created or destroyed. The total amount of energy is constant. Energy can be changed from one form to another form. It can be transferred from one object to another object, but it can't be created out of nothing, and it does not vanish into nothing. So the energy that you use to power your whole body came from the food that you eat. The food that you eat had stored up energy in it. Now, where did that energy come from? The food that you ate stored up that energy either from the sun, if it was plants, or by eating plants, if it was an animal, or by eating other animals, if it was a predator animal. And so energy gets transferred. And when you eat some food and you use some of that food energy to, make some new molecules and to store up some ATPs, you're also releasing a lot of that energy to just body heat. In fact, on the coldest day of the year, in the coldest, snowstorm, with no clothes on, you could stay warm by drinking an ice cold soda, and it has to be a sugar soda. It can't be diet soda. Because the energy that you're going to get from breaking down that sugar in glycolysis in your body is going to liberate so much heat that you're going to stay warm. Don't try it, but try it. It'll work. Okay, so energy can be transferred. Let's talk about the different ways that energy can sort of exist. Sorry, I shouldn't have skipped. So we have something called kinetic energy. Kinetic energy is energy of motion. Anything that's moving has kinetic energy. We can have potential energy. Anything that has position or composition can be called potential energy. So for example, a spring has potential energy in it. We could also call that mechanical energy if we had to compress the spring. But a spring in general has some potential energy associated with it. Think about a book sitting on a shelf. If you have a book sitting on a low shelf, that's got some amount of energy. Gravity wants to pull it down, and if it fell down off that shelf, it would hit the ground with some amount of force. Put that book in your mind up on a higher shelf now. It's got more potential energy, right? Would you rather get hit by that book when it falls off the top shelf or off the bottom shelf? You know the answer to that is the bottom shelf, because if it falls off the top shelf, it's going to hurt more because it's got more energy in its position. Gravity can work on it longer, therefore it can speed it up faster. So that's potential energy. There's electrical energy, the kind that you store up in your feet when you walk across the carpet with your socks on and then touch your little brother in the face. There's thermal energy. This is the energy associated with the random motion of atoms and molecules. And while I am saying thermal energy, I want to throw this out there. Thermal energy is what we measure as temperature, but what temperature is a measure of? Motion of particles. You may think that it's the temperature that affects the motion of particles, but it's not. What the temperature is a measure of the motion of particles. It makes sense, yes, if you make the temperature hotter, that particles move faster, but the only reason the temperature went up is because the energy we put in made the molecules move faster. The temperature isn't a thing, okay? Temperature is a reading. When we go and turn the fire on under a pot of water, the fire doesn't go and make the water hotter and then the molecules go, hey, it's hot in here, let's start boiling. Do you know what I'm saying? Like the water got the fire right off the bat. The fire is going into the water and making some of those water molecules move around a lot faster. And when the whole collection of water molecules starts to move a lot faster because of all the heat it's getting, all of the energy you're putting in, they suddenly say, hey, I don't need to be a water molecule anymore. I can be a gas molecule, and they boil. So, and actually that has to do with the pressure. They have to overcome the miles of air that are sitting on top of that pot of water, holding it down. And we'll talk about pressure when we get to the gas chapter. Okay, so thermal energy is the motion of particles. This is why there's no such thing as absolute zero. Because if there are particles, even one atom, there's a moving electron inside that atom. And if things are moving, then there's a temperature. Okay, lastly, there is chemical energy. Chemical energy is a form of potential energy associated with the position of particles in a chemical system. Okay, let's talk about the units of energy. Units of energy, the SI unit that we use is actually called the joule, named after the English scientist James Joule. He's the first one who actually demonstrated that energy can be converted from one type to another and that the total energy was conserved. So he's kind of like Lavoisier in that he helped contribute to the conservation law. The second unit of energy is called the calorie. You're more familiar with this one. The calorie comes with a little c. Then it also comes with a big C calorie. A big C calorie is 1,000 little c calories. We can also convert a calorie into joules. 4.184 joules is 1 calorie, and both of these are the energy that it takes to make 1 milliliter, or 1 centimeter cubed of water, which, by the way, weighs 1 gram. We define that for water. We raise this by 1 degree Celsius. So 1 gram of water, or 1 cubic centimeter of water, changing by 1 degree Celsius, the energy that it takes is 1 calorie. So that's where all that comes from. Now, big C calories are what you have on your food bags. Kilowatt hour, this is how, if you pay electricity, we get billed for our electricity. There's 1 kilojoule per second, and there's 3,600 seconds in an hour. So a kilowatt hour is, and a watt is a joule per second. So that's the part that you didn't get here. Big watts, that's joules per second. And kilowatt means that, right, we're talking about 1,000 joules per second. And so then 1,000 joules per 3,600 seconds in an hour gives us a kilowatt hour. Anyways, I think like average cost of electricity is about 12 cents per kilowatt hour, or like 14 cents per kilowatt hour, something like that. Okay, conversions. You got to be able to do energy conversions, or converting between different different units of energy. So let's give one a shot. So let's say a candy bar contains 225 big C calories of nutritional energy. How many joules does that contain? So we need to go from calories to joules. We need to figure out, is there a direct calorie to joule conversion? No. There's a calorie to calorie conversion, where 1 calorie is 1,000 calories. It's a big C calorie. And then there's also that 4.184 joules is 1 little calorie. So we've got those two things to work with. So we'll set up our problem as 225 calories. I'm going to take my big C calorie and turn it into some little c calories first, and then take my little c calorie and turn it into a joule. The units should cancel out, leaving me only joules. And if you do the math right, we'll worry about the sig figs too. There's 3 sig figs in this number, so calculate this out. It should be 9.41 10 to the 5 joules. Um, yeah. So that's a lot of energy. Now, I have a table somewhere here, or there's one in the book that kind of shows you how much energy you go through in a day and that kind of stuff, which is neat to look at. Um, there are other classes that you can take later on in your careers. If they deal with energy, you end up finding out just how much energy like a city uses, and then how much energy is actually stored up inside nuclear bonds. Like if we could use, like when you talk about nuclear energy and the benefits of it, you get so much more energy from it. We could burn 1,000 pounds of coal and get so much energy from it, or we can take one little nugget of coal, and if we could get all that nuclear energy out of it, it would actually power a whole city for a day, like that kind of stuff. So it's neat when you start looking at energies and kind of comparing things, but that's not the goal right now. So that was just a conversion between calories and joules, and those are important because sometimes you're asked to find an answer in joules and you're given calories, and so you want to practice those. All right, so potential energy of a waste rate. I mentioned a book and how you can think about the higher a book is on a shelf, the more potential energy it has. We like to use this analogy also to kind of give us an idea of what direction reactions like to go in. Some reactions like to lower their potential energy, and some reactions will actually happen and raise their potential energy, and those are what we would call um, endergonic reactions. I can never say it right. I'm always pronouncing it wrong. They're non-spontaneous reactions that require heat in order to make them happen, but they do happen, and so our body is full of those types of reactions. So they're worth mentioning. But nature really does tend towards lowering energy, and so the spontaneous reactions, the one that happens on their own, like a deck of cards falling and becoming unshuffled, right? That happens more often than a deck of cards shuffling itself back into a perfect order, right? That doesn't happen. You have to put energy in to fix a deck of cards that's out of order, but you don't have to put any energy in to make a mess. And that's what nature does. We call that entropy. It's a kind of a tendency towards disorder. And that's kind of what happens. And so here we see the same thing. If we have a high potential energy, we can think of it as unstable, and that by lowering its potential energy, it's become more stable. And so we can draw some energy diagrams to kind of represent this. The first energy diagram I want to show you is one called exothermic, and it kind of relates to the picture I'm showing you here. We start off with a reactant that is higher up on the energy scale than the products that'll happen after the energy gets released. And so energy being released, this could be the chemical reaction happening, but we end up with products that are lower on the energy scale. When energy is released in this process, we call it an exothermic reaction. Dissolving sodium hydroxide in water, for example, is exothermic. If you dissolve sodium hydroxide in water, the water gets really hot. Chemical heat packs, right, that you break and you just shake up and they get really hot, these are exothermic reactions. Endothermic reactions are the opposite. These actually will cool down if you dissolve, I think it's ammonium nitrate. I think it's ammonium nitrate. If you dissolve ammonium nitrate in water, the solution actually gets colder. It gets colder. It absorbs energy to get those molecules to dissolve. The solution loses energy, and we feel it getting colder. That's called an endothermic reaction. These terms also mean something. Exo is out, endo is in. So thermic is heat, right? Exothermic means out heat, or heat goes out. So that's released, right? Endothermic, heat in heat. So if heat's going in, it requires energy to happen. It's absorbing energy. We call it endothermic. Systems with high potential have a tendency to want to lower their energy. Some chemical substances, such as molecules like TNT, have really, really high potential energy concentrated in them. Another one in our bodies is ATP, adenosine triphosphate. This molecule is what we call a high energy molecule. It basically is a molecule that is unstable, and so by becoming more stable, it's able to power all of the reactions in our body that would normally cost energy to happen. Okay, let's see. Let's talk about temperature. So thermal energy, constant random motion of matter. So random motion leads to just thermal energy. And again, When we stick a thermometer in the room, what we're feeling, what we're measuring is how often the molecules of gas in the room are bouncing around and colliding with the little liquid inside, or the glass around the little liquid inside that thermometer. And if the molecules are bouncing around a lot and colliding a lot with that glass, then they heat up the glass in the sense that they start transferring their collision energy into the molecules of the glass, which start to vibrate more, which start to transmit energy into the liquid that used to be mercury but now is an ethanol solution inside the thermometers. And then the thermometers start to, the liquid inside start to expand, because as they gain energy, they start to kind of move away from each other, and they expand a little bit, and they end up, the thermometer value changes, right? Digital ones work a little bit differently, but yeah, so it's motion of molecules that we are calling temperature. The hotter an object, the greater the random motion of the atoms and the molecules that compose it. When you get an object that's really, really hot, it's vibrating so much that actually it can start giving off light. And we'll talk about that when we get to chapter 7. Heat. Heat has no units. It's the transfer or exchange of thermal energy. Transfer of thermal energy. So for example, when a piece of cold ice is dropped in a cup of warm water, right? Bloop. Which way does the heat go? The heat always transfers from high to low. So warm water is going to start sending its heat towards the ice. And as those ice molecules, right, the solid starts to gain those heat molecule, or that heat energy, they're going to start to vibrate a little bit more and become liquid, and they're going to be able to move past each other, and that's what melting is. So temperature is a measure of the thermal heat, not the exchange of the thermal heat. Heat is the exchange. I shouldn't have said heat, I should say energy. Heat is the exchange of energy. Temperature is a measure of that energy. Okay, let's talk about the scales that we use to calculate temperature. So we've got the Fahrenheit scale. Now this one assigns 0 to the freezing point of a concentrated seawater or saltwater solution, and 96 degrees to a normal body temperature. So randomly, that's what it assigned, whatever to. That doesn't match anything, right? Because the 0 degrees Fahrenheit being a concentrated saltwater solution doesn't even match the actual temperature water freezes at. So Fahrenheit is just overall a bad scale. We shouldn't look at it at all. We should just ignore it. In fact, if we look at Celsius and Kelvin, you see that they're good for a lot of reasons. One, Kelvin's the best because it has a 0, right? We don't have to deal with negative numbers. Kelvin's the best. Second, Kelvin and Celsius both have the same size degrees. So from water boiling to water freezing, there's only a difference of 100 degrees, or there's exactly a difference of 100 degrees. So it doesn't really matter what the number is. If we say, oh, it changed by, that's what this triangle is, delta, it changed by 3 degrees. Does it matter if it's Kelvin or Celsius? No, because the size of the degrees are the same. Changed by 3, whatever. It's 3 degrees colder, it's 3 degrees hotter, it doesn't matter which scale we're using. That's not true over here. The size of a Fahrenheit degree is clearly different than the size of a Celsius degree. 1.8 Fahrenheit degrees equals 1 degree. So we've got some conversions. Now to go from Kelvin into Celsius or vice versa, Celsius into Kelvin, we need to take Celsius plus 273.15. That'll give us Kelvin. Kelvin back to Celsius is just going to be minus 273.15. Now for Fahrenheit, Celsius is Fahrenheit minus 32 over 1.8, and Fahrenheit is going to be 1.8 degrees Celsius plus 32. So you should practice these temperature scales, practice using them, get in the habit of using Celsius and Kelvin, because those are the scales that we're going to mainly deal with. We'll deal with Kelvin in the gas chapter, because there's a lot of equations. For example, we have like V1 over T1 equals V2 over T2, right? If the temperature is in Celsius, well, what if it's 0? Well, then we can't do that equation, right? You can't divide by 0. That's why we're going to use Kelvin. for the gas chapter, because we won't have to deal with a zero value. A zero value of Kelvin means that there's no molecular motion, nothing's moving. And so far, as long as there's a universe, there's things moving. So, yeah, we're going to get into using Celsius and Kelvin, but Kelvin mainly for gases. Let's talk about heat capacity. So the heat capacity is the quantity of heat, usually in joules, required to change the temperature of a given amount of substance by 1 degree Celsius or Kelvin. So, and you can kind of see that here. So, so we can define it like this: 1 gram by 1 degree Celsius. Okay? Whatever will change the temperature of 1 gram by 1 degree Celsius, we need to see how many joules that was, and that's the specific heat of the substance. So for lead requires 0.128 joules for every gram to change it by 1 degree. Silver requires more energy. Water requires a ton of energy, right? If you had a pot of water on the stove, right? That's your burner. Your knobs. Okay, you got a pot of water on the stove. You turn it on. Fire. You wait 10 seconds. What are you going to touch? You going to touch the outside of the pan, or would you stick your finger in the water? You have to do one of them. Which one are you going to do? You're going to stick your finger in the water. Why? Because you know the water's not even hot yet. You know that the water takes a long time to get hot. You know that it doesn't take any time at all for the pan to get hot. The pan, if you've got good cookware, it's made out of copper, only takes 0.3 joules for every gram to start changing by 1 degree. Water, on the other hand, for every gram of water, it's going to take 4.184 joules. That's what, like, 10 times as much energy? This is a really good thing for people to live at the coast, right? The water there actually absorbs a lot of the heat from the sun. It absorbs a lot of the heat, and so as a result, the temperature doesn't change that much there during the day, or over the course of the year even. Okay, so let's talk about what we would do with heat capacity. So for one, we could use this to identify a substance. If we could identify the heat capacity of an object, well, heat capacities are just like densities. They're specific to materials. And so having a little list of heat capacities would let us identify an unknown. Now you see gold and lead actually have the same heat capacity, so we'd have to go by color and other things there. What else? We could use the heat capacity to see how much heat something could absorb, or what the final temperature of something would be. We are going to do a whole lab on this, and so you're going to get some practice doing these, but let's talk a little bit about the equation, and then we'll do a practice problem. So in the equation, Q here is going to be the amount of heat. So Q is heat. M is the mass, and the mass is going to be given in grams. Needs to be in grams. So if you're given a mass in kilograms or ounces, you need to change that. We've got Celsius as far as the temperature goes. Could be Kelvin, doesn't matter. Delta here just means the difference of temperature. So Kelvin and Celsius, we know, are the same size. C, which people often think is the Celsius, right? Because the degree thing, there's no degree here. This is the heat capacity. So that's these guys and all of their units. And if you plug all this stuff in together, you end up seeing that it's something mass, or here, let me do it this way. It's something grams times joules over grams degrees C times some kind of degrees C. Grams cancels, degrees C's cancels. This is why heat is in the unit of joules, okay? Or calories. It can be in calories. Sometimes we have specific heats that are calories per gram degree Celsius, at which point this would just be calories, and then calories would be your answer. And that's okay. You can have calories. Okay, I think we should do a problem. So gallium is a solid at 25 degrees Celsius, and it melts in your hand at 29.9 degrees. If you hold it in your hand. How much heat must the 2.5 grams of gallium absorb to raise its temperature enough from 25 to 29.9 so that it can melt? Because it'll melt at 29.9. And they told us the heat capacity. Okay, so let's organize our data. Let's see what we have. So gallium is a solid at 25. It melts at 29. Okay, so let's see. That's not really anything. We keep going. Grams of gallium, 2.5. So mass, 2.5 grams. Okay. It raises temperature from 25 to 29. That sounds like a delta T to me, if I've ever heard one. So it raised its temperatures by what, 4.9 degrees? The specific heat capacity of gallium is 0.372 joules grams degrees Celsius. If we go back to our equation, we see that we have mass, we have C, we have delta T. We don't have heat. And this says how much heat. So we know what we're doing. We're going to plug everything into our equation straight in. We're not going to rearrange. We're not going to do anything. So Q is equal to 2.5 grams times the heat capacity. That says for every gram, for every 4.9 degrees Celsius, it's going to take 0.372 joules. So then you plug it in, you solve for it, we're going to get 4.557 joules. We got to go back to our sig figs. We see we got 2 sig figs, 2 sig figs, and 3 sig figs. This is multiplication division problem, so 2 sig figs. We're going to round. So this would take 4.6 joules. Now, this is what it takes to raise the temperature, just to be clear. This is the amount of heat it takes to raise the temperature to the melting point. It actually takes an additional 200 joules. Yeah, 200 to actually melt the gallium. But we'll talk about that in chapter 12. Melting the gallium involves breaking the bonds that are holding the atoms together so that they can move away from each other. What we did here was just calculate how much heat we had to put in to get it to the right temperature. It melts at 29.9, but it was at 25. We wanted to warm it up to 29.9, and that takes 4.6 joules. Okay, so in this chapter we looked at matter. We looked at classifying matter as pure or as an element or as a compound. We looked at mixtures, homogeneous, having the same composition throughout, heterogeneous, having varied composition throughout. We looked at physical and chemical changes, physical properties, chemical properties, those that change the substance or don't change the substance. We looked at conservation of mass. We looked at energy and how it's conserved, can't be created or destroyed. We looked at the joule, the calorie, the big C calorie. We talked about exothermic and endothermic. I explained how temperature works, what heat capacity is, and given you guys a list here of the learning objectives. So good luck with this chapter, everybody. Let me know if you have questions. Please attempt the homework. This is chapter 3, so you guys should be working on the chapter 3 homework, all on mastering chemistry. And yeah, good luck. Do practice problems. Let me know if you have any questions, and good luck. See you guys next time.